thought I'd have a look here at the differential calculus calculator section questions from last year. Now, of course, with these questions, you've got the calculator available, but it's advisable to only do that maybe to check answers or to do things that you can't really work out by hand, that you have to use a calculator for. So here's a classic example here. We've got determine the derivative of y equals x to the power of e over log x to the base e. Interesting question, this one, because we haven't really dealt with this x to the power of e much in class. It sort of didn't come up in the textbook very much. So there's nothing to worry about, because remember, e is a number, 2.713, whatever it is, and it just acts like any other number in that sense. But anyway, so I've nominated here my u and my v. So the u is the numerator, here it is here, x to the power of v, and v is the denominator, log x to the base e. And we get the derivative of both of those. So when we get the derivative of x to the power of e, of course the e goes out the front there. There it is, it goes out the front, and then it gets reduced by 1. So it becomes e x to the power of e minus 1, because if we're reducing e by 1, it becomes e minus 1. And we know the derivative of log x to the base e is 1 over x. So then we apply the quotient rule, because we've got two expressions that in a division situation there that we're getting the derivative of. And you can see I've applied the rule there. So it's du dx times v minus u times dv dx over v squared. So I've applied the rule there. Now, next thing we have to look at then is, once we've done that, how we simplify this left-hand side. The numerator. So you can see the only real thing I've worked out going from the first line to the second is, I've multiplied out there, so x to the power of e times 1 over x is x to the power of e over x when we expand the brackets there. And I've missed out a square down below here as well, I just noticed. So there we go. Alright, we'll go a bit further with that. What I've done then, go from here to here, you'll notice that I've made x to the power of e over x, x to the power of e minus 1. Because remember, x by itself is x to the power of 1. When we divide, we subtract indices. So if we've got x to the power of e over x to the power of 1, it becomes x to the power of e minus 1. When we divide with indices with the same base, we subtract. Then, going from here to here, I've taken out a common factor. So you'll notice in both expressions I've got x to the power of e minus 1 there and x to the power of e minus 1 there. So I can take it out as a common factor. There it is. If I divide it into the left-hand expression, let's get rid of all these boxes now. If I divide this into, the left-hand expression here, all of that, I'm left with e to the power of log x to the base e. If I divide this into here, I get negative 1. So remember with your division there. Just a general principle there that we sometimes have, I've seen us get caught out on before. If we've got ax minus x, for example, and we take x out as a common factor, it's x outside of a minus 1. Sometimes people think that just disappears mysteriously, but remember that factorisation. It's really important. Okay. Let's get rid of all that. So there's our answer. We can't really go any much further with that once we've factorised it. So that's the answer down below here. Here's our answer for that first question. Next question, find all stationary points of y equals x cubed e to the power of x. So to find stationary points, remember we make the derivative equals 0. So to find the derivative, I've used the product rule. Okay, so we've got our u, which is x cubed, and our v, which is e to the power of x. The derivative of x cubed is 3x squared, and the derivative of e to the x is e to the x. So I've applied the product rule there, and then I've factorised going from here to here, taken out to x squared, e to the power of x common factor. If I take x squared, e to the power of x out of there, I'm left with x, okay, because x squared into x cubed is x. If I divide it into here, I'm left with plus 3. So that's how I get the factorisation there. Now I make that equal 0 to find stationary points. You make that equal to 0. Now it's a bit tricky here. Okay, now we probably by now would have enough experience to see that the solution of the bracket there, x plus 3, is neg 3. What about all this stuff outside here? Now remember, e to the power of x, e to the power of anything is just a number, so it's something x squared. And I think I've pointed out before that, you know, if you've got a situation where, for example, you've got 3x squared outside of x minus 5 equals 0, the two solutions there are 0 and 5. They're the two solutions. Okay, anything x or anything x squared outside a bracket, one of your solutions is 0. The other solution comes from the bracket itself. Okay, so effectively in that red square that I've got there now is something x squared, some number x squared. So that solution will be 0. Because if x is 0, let's make sense of this, if x is 0, all of that in the red square is 0, which makes the whole expression 0. We've got an equation happening there. Alright, what I've done here on the right hand side, now, look, I'll just put a star here. So what I'm doing over here is finding the y coordinates. To find the y coordinates, we put the x coordinates into the original. You can pause the video here at this stage and have a closer look at that. But I get y coordinates here of 0 and negative 27 e to the power of negative 3. So I've now got my 2 points. Should put brackets there. 0, 0 and neg 3, comma neg 27 e to the power of negative 3. So we've found the stationary points. So we've done this part of the question. Find all stationary points of that. Now we have to determine their nature, which is the next thing here. And to do that, we set up a gradient table. Remember, we put our x coordinates of our stationary points here, and around about those points, we find points that are lower and higher than neg 3, and then obviously lower and higher than 0. And we place what I've put a green square around there. We place those values into the derivative, and you can see that I've done that down here. When I put x to the power of negative 4 in the derivative, I get this. Now careful here, you might think, oh, there's two negatives multiplied together. But remember, e to the power of negative 4 is not a negative value. Okay? It's not a negative value. So, what I'll get there is negative 1 times a positive value, in fact, which means it's negative overall. And that's why I've got negative here for neg 4. So when I put neg 4 into the derivative, I get a negative value. What about negative 1? Okay, same thing. I get something like this, remembering that e to the power of negative 1 is not a negative value. It's positive, and you can put it in the calculator if you wish, if you're not sure about that. So that expression here, that is going to be a positive value, hence I've got positive there. Same over here, when I put 10 in, that will also be a positive value. So there's my gradient table, and I've put in my slopes there, and you can see that clearly 0... Oops, I think I got that the wrong way around. Just a moment. No, I didn't. All good. I had it the right way around. A bit confused there, but you can see that around negative 3, I've got negative 0 positive, and that distinctive shape there gives me the minimum. Alright, so that's a minimum. Around 0 here, I've got positive 0 positive. You can see I put that there. And that gives me a positive point of inflection. In other words, it's something like that, where it's positive gradient, 0 gradient momentarily, then positive gradient again. So there's my two stationary points. Okay, these tangent questions can be a bit tricky, but if you know your way around them, you can pick up some good marks here. It's worth 3 marks. Okay, so the function 2x squared plus 3x plus a is a tangent 5 minus x. Determine the value of a. Right, there's a few distinct steps here. The first thing we know, and because of the rule y equals mx plus c, we know the number in front of the x is the gradient. So if If we've got y equals 5 minus x, what's the number in front of the gradient there? It's negative 1. That's what the gradient of the tangent is. Okay? So, from there, what we have to do is find out the x-coordinate that tangent is. Okay, so we've got this, just to paint the picture here, and I probably should have done this beforehand, but we've got this quadratic, 2x squared plus 3x plus a, and we've got this tangent, which is 5 minus x. It's got a negative gradient, so it's something like that. So that's the point that will be common both to the tangent and the curve. All right? All that we know at the moment is that the gradient of that tangent is negative 1. We can now find, though, what the x-coordinate is where the tangent touches the curve. Because if we look at our gradient here, it's 4x plus 3, and we get that from here. Remember, the derivative gives you the gradient, so that's the derivative. F dash x is 4x plus 3. Okay, and that gives us the gradient, and our gradient is negative 1. If we make them equal each other, like I've done here, we can actually find the x-coordinate. So I've found it there, x equals negative 1. Okay, so it's negative 1 comma something. Okay, and to find the something, remember we've got two lines here. We've got our 2x squared plus 3x plus a. We've also got our 5 minus x. Okay, so negative 1 lies on 5 minus x. So if I put negative 1 in for x, okay, if I put negative 1 in for x, I find my y-coordinate. Okay, and it's 6. So that point there where the tangent touches the curve is negative 1 comma 6. So there we are. Now, how do I find a, which is the purpose of this question? I now substitute in here. I put 6 in there, and I put negative 1 in for x there and there. You can see I've done that there, and then I can eventually find a. Okay, next question. A factory produces cylindrical cans. To reduce cost, each can is made with a surface area of 96 pi square centimetres. And you can see here you've given the two formula here for surface area and volume. That's why I allowed you to have that formula when we did the test for this, because I'm 90. What am I? I reckon I'm 95% sure that they will provide any of these volume and surface area formulas as they have here. Okay, so it says show that the height of the can is given by 48 minus r squared over r. Well, we know the surface area, S there, we know that's 96, whoops, sorry. We know that's 96, draw an arrow there, 96 pi. So you can see what I've done there is I've substituted in 96 pi in for S. Pause the video if you wish, you can work your way through, and eventually we get to there. Last step, of course, we want to get everything over r. The 48 is already over the r, but this little negative r here is not already over r. So to get it over r, we've also got to multiply it by r. Okay, so you multiply the term that's not over the denominator by that denominator. So we get 48 minus r squared over r equals h, which is what they've got there. Next part of that question says determine the maximum volume of a can. V equals pi r squared h. Now we're just told that h equals 48 minus r squared over r. And of course that's handy because we've got two variables here. We've got r and h. And remember when we do these to get the equation for volume, we really only need one variable. So by substituting h for the value over here that we're given, we can now get... you can see here, we can now get a formula for volume. So once again, pause the video at this stage if you wish and work your way through it. Crucial thing here is that, let me see, I've cancelled. You can see here I've cancelled r with r squared there. So that's why you just get the one r there. Then once we've got that equation for volume, remember, to find maximum volume, you make the derivative, which is that, 48 pi. Okay, it's the number in front of the r. Remember, pi is a number, not a variable. Minus 3 pi r squared. The 3 goes out the front, reduce the index by 1. We make that equal to 0. Okay, you can take 3 out there as a common factor if you wish. But nevertheless, you get it down to r squared equals 16. which means r equals plus or minus 4. I haven't written it in here, but you probably should here, by asterisk there, you should mention why you reject negative 4. You can't have a radius of negative 4, so you reject negative 4. I probably should have written that in, so make a mental note to do that. Okay. Then to find maximum volume, once you know that r equals 4 for maximum volume, you've got your equation for volume, a couple of slides back, and you substitute the 4 in for r to get the maximum volume. And don't forget, because it's volume, it's units cubed. If it was area, it would be units squared. Alright, so that's a bit of an overview of last year's differential calculus section. In the calculator section, it was probably, out of the different calculator section, probably the easiest, although it had a few little tricks to it.